All right. Awesome. So thank you all for joining. We are going to talk planning for serial scan today. We have Sam Rosen, our strategic marketing manager, and he is going to lead our presentation. So I will pass it over to you now, Sam.
Hi, everyone, and thanks so much for joining us. And Kaylee, thank you for the introduction. As she said, we're here to talk about serial scan. I know that serial scan is something on people's mind, but maybe something they don't feel they have adequate information around. We've been working on serial scan for on top of 2 years in terms of implementation and planning, working with lead customers. So it's something that we have a good amount of experience with, and we wanted to share some decision points for semiconductor OEMs around serial scan. So to really frame the discussion, I think it's important to start here. Most commonly, the first slide you'll see is a chart that shows how the scan data volume or test time, number of flops per device, is going up and to the right. I didn't want to speak there because it doesn't necessarily show exactly what happens underneath that. And so this is maybe the next level of detail below that, and why is scan failing, the technical capabilities and growth curve, and economic demands of testing parts. So the first reason is that there are, in modern semiconductor devices, as you move to advanced process nodes, 10 nanometer, 7 nanometer, 5 nanometer, and even up into the 12 nanometer nodes, and etc. There's less GPIO. That's a function of both the way that interfaces have shifted over time, and packaging trends. So in mobile devices, you have package on package for memory integration. In advanced server parts, you're shifting to 2.5D and 3D packaging, including high bandwidth memory. And so there's generally less GPIO pins available. On the upper right, the rate at which you can shift chains through your part is limited by a combination of power considerations and thermal considerations. And some of these relate to burning up the part, some of these relate to the ability of the tester to supply power at the chip, based on the number of pins or number of pads, or the test environment that you set up. And so the scan frequency is relatively fixed. There's been this promise that ATPG tools could improve, and ATPG tools have improved and can improve and do improve, but it doesn't really keep up with the curve, so you have test times increasing. Hierarchical scan helps a little bit, but it's applicable primarily to designs where you have the same core instantiated multiple times, and so not every device can take advantage of that. And then on the bottom right, the test time, as we spoke about, is going up. The biggest factor here is long scan chains, which is a function of as many GPIO pins as you can devote to it. GPIO pins both require pads on the package, and also the routing on the tester becomes complicated. The number of tester pins you're devoted to it is high. And so it changes it. So serial scan, the one thing that it fundamentally does is it breaks that dependency between the number of external scan pins and internal scan chains. And that gives us the capability to bend the cost curve. So in general, there are two different approaches to serial scan today. There's low protocol scan, most commonly associated with IEEE 1149.10, and there's high protocol scan, which can operate on USB or PCIe interfaces. So low protocol scan is the protocol refers to the amount of software or sort of the complexity of the state machine that exists in the IP on the chip. So low protocol scan tends to be very ATE centric. It works very well with a standardized interface like JTAG did. It has easy bring up on the tester. It generally requires minimal IP and software investment. The controller you put in to distribute your scan chains is relatively simple piece of logic. And it has minimal changes to the test flow, primarily around mapping virtual chains to logical chain requires some additional challenges. On the right side, the high protocol scan has some additional benefits for customers that are using system level test. There's this strong portability of a test between an ATE environment and SLT environment, and even the ability to execute in system test or power on self-test in applications like automotive. It requires dedicated IP and software. From an IP standpoint, you're often effectively integrating the test controller with a piece of relatively complex system IP like a USB controller or a PCIe controller. But it does provide this consistent debug environment between bench, ATE, and SLT. So as you adopt this, you see the intensity of some of these colors shows how the technical challenges change. In a nutshell, you're switching from a bandwidth limited design to a power supply or thermal limited design. You're adding complexity of serial interface and asynchronous operation as you move into both low protocol and high protocol scan. And the ATE environment shifts from standard to highly customized. And so there's tighter integration between the EDA company and the tester platform that has to be done as you move. And in terms of tester resources, you move from using a few very low-cost general purpose many low-cost general purpose resources to using a few simple resources. Here I'm going to take a second and really just make sure that everyone understands the basic premise of how the pins change and economics change in this environment. So an example design has 80,000 flip-flops, and the thermal shift limit and power delivery and thermal shift limit on the tester is 100 megahertz. The ATPG tool has been run and optimized. There's some knobs you can tweak on this that also alter the toggle rates to try and put more ones and zeros together. And that curves the power. Let's assume that that's been used. But effectively, there's 2K loads to achieve this specified level of fault coverage that's your design target. So in the legacy case, you had 40 chains with 2,000 flops on each chain, limited by how many GPIO you were willing to dedicate to route out, you had access to, as well as tester resources. And so externally, you have this one-to-one mapping. And so the bandwidth you had is 4 gigabits, full duplex bandwidth on the scan-ins and scan-outs driven by that. So if you do the math, how many loads you have divided by how long it takes to load each chain, and at the frequency you're driving, you have about 40 seconds of load unload time. And just to be simple, I put about a second of test execution. Often you're running a quick clock command on the JTAG after you do the load. And so there is a little bit that's fixed on top of the shift, the load unload time. As you go into the low protocol case, you might triple the number of internal scan chains. So you go from about 2,000 flops to 667, right? Externally, you may be using 8 pins here, 8 scan-ins, 8 scan-outs at a frequency which is 16 times as much. And so this gives you external bandwidth of 12.8 gigabits per second. And you're able to bring the test time down, or the shift time down by a third. and your test time not quite that much because of that overhead. So you get to about 15 seconds. In the high protocols case, you're using a USB port. And in this example, we assume the USB 3.1 Gen 2 port, which has 10 gigabits of full duplex bandwidth. And so similar to the low protocol case, a little bit slower because you're bandwidth limited, but basically the same situation on one pin instead of 8 pins. Running at 10 gigabits does have signal integrity challenges in the tester environment that we have worked with customers and our test instrumentation to solve. So I spoke before about the collaboration that's required in serial scan. What are the roles and responsibilities of each party? The semiconductor OEM needs to focus on the chip architecture, how the scan chains map into IP blocks, and doing the insertion, making sure to do the validation, diagnostics, and debug plans to make sure that the IP is verified, everything is stitched, the stuck-at coverage can be achieved, in simulation. And then making sure that whatever IP you choose, scan interface, scan implementation you choose, matches the resources of the tester capability that you plan to test your device on. I'll go to the right here. The EDA vendor provides scan controller IP, helps to provide the ATP generation and insertion flows, and provides validation workflows and a test bench. And then the ATE vendor and or test engineer are responsible for pattern conversion and data collection, providing debug tools to bring up the device, providing the advanced high-speed serial instrumentation and guidelines like DIB routing guidelines to make sure that you achieve the signal integrity, make sure you map to the resources that have the adequate depth behind them, and support any specialized modes that might need to be used. And then it's also very important today. Another thing that's happening with scan is we see a lot of data collection happening in terms of scan map failures. And sometimes this is used for advanced binning workflows. Sometimes this is used for advanced fault analysis and debug workflows. But the tester architecture has to support a lot of data passing. And our current generation UltraFlex Plus platform has a tremendous bandwidth at the tester. And so that's something that's been helpful in that regard. So in summary, we're here to engage, to prepare for serial scan implementations, regardless of whether you choose low protocol or high protocol. The low protocol has this sort of easy, classic ATE focus, and we've worked with tester-based instrument integration and verified devices in the low protocol case. And in the high protocol case, you have this additional benefit of seamless ATE SLT portability. We have a PC-based instrument shipping, as based on the example, supports USB 3.1 Gen 2. And so it does take the semiconductor OEM, the IP and ATPG vendors, and Teradyne collaborating to bring you serial scan. So that was our presentation for today. I'm going to turn it over to Kaylee and Roger to see if any questions have come in, and I think Roger was going to answer those.
Yeah, I think I'm just taking a look and I don't see any questions that came in, but on the first slide, Sam did provide his email, sam.rosen@teradyne.com. If you have any questions, feel free to reach out to him. And otherwise, please visit the Teradyne website, teradyne.com/AI, where you can find some more helpful information and also submit your questions there to our sales team. So that concludes our LinkedIn Live for today. Appreciate everyone who joined, and we'll see you next time.
Thanks very much.